Well, thank you all for coming. Really great to see some familiar faces and some not so familiar faces. I really appreciate everyone coming out. I gave this talk in Sydney to speak up, talk louder. Okay. I gave this talk in Sydney a few weeks ago to a packed house, and it went well. So I'm hoping I can at least replicate that tonight. But what I'm really talking about, I'm a sort of geophysicist / structural geologist / mineralogist / GIS person. I don't necessarily claim to do any of it really well, but what I'm really about is trying to integrate all these different types of data together to get an understanding of mineralization and how it manifests in geophysics. So I'm going to take you through some work Dave Clark and I probably did first maybe 10 years ago, and some work we've built on since then, and some simple hacks for differentiating ore systems in geophysics. And as I started doing this, I realized it's probably not all that simple, but hopefully it'll be an entertaining talk and you'll get something out of it. Okay, so what we're going to talk about, deposit models, so geological ore deposit models, pros and cons, how we do geophysics, what's petrophysics. We'll look at some of the sort of typical sort of targeting strategies, like the coincident anomalies, co-located sources, try and link paragenesis to petrophysics, and then look at some different types of zonation, and then some of the really hard stuff right at the end. If everyone's not yawning by here, I'll go into that, but we're getting into tricky stuff there. So, disclaimer, these are just models. They share all the complexities of geological ore deposit models. These are just the geophysical variants, and they're really just working hypotheses for targeting specific ore deposit types. And obviously all models are wrong, but some are useful, and keep that in mind as we go. So pigeonholing deposits or ore deposit models, I guess it's a necessary practice. It gives us a lot of good things, useful things, helps us recognize commonalities and links between deposits, provides generic models of ore deposit formation. It gives us temporal frameworks for understanding ore genesis, and it gives us spatial frameworks for understanding zonation of metals and alteration halos in mineral deposits. And there's some really good, very well-known ore deposit models to see here. So for VHMS type deposits, the classic porphyry deposit, and there's all sorts of different models for IOCGs, depending on which one of the IOCGs you're talking about, but starting with Hitzman back in '92, I think. So there's a lot of pros. It gives us information about processes, so tectonic drivers, magnetic drivers, structural controls, fluid chemistry. So these are the sort of the 5 mineral system ingredients that we used to talk about in the PMD CRC many years ago. And they also, as a consequence, give us exploration criteria. And that means we're armed with knowledge. This is what we think we're looking for. We've got a whole bunch of different types of data sets, going from very broad scale data sets, very regional crustal scale data sets, deep data sets up to shallow in the geophysics there. And then we've got characterization data sets up here. So we work our way down the exploration pathway to about somewhere around here, and then we work our way back with this knowledge. The great thing that geophysics gives us that some of these other data sets don't is that most physical properties are scalars. And that means if we can basically invert these petrophysical properties to geophysical fields and vice versa. So they scale naturally, provided we get the right resolution. So we don't have to worry about kriging and all that kind of stuff. We can actually, if we can understand what's happening in our mineral system and link it to physics, we can actually do things a different way. So some of the cons, and this is just an example of a porphyry system here, and you can see related to this, we've got skarn deposits, we've got epithermals, and a lot of this can be actually within one broad alteration halo. So the problem with some of these models is, they can be too specific or too generic. And they really struggle where we have overlapping mineralization styles within a mineral system. And so Cobar is a pretty good example of that. And many of you may not be all that familiar with Cobar, but I might go there briefly. It can also be a problem when you've got overlapping mineralization styles within a deposit. And we also see that in a number of instances in Cloncurry and Cobar, as I'll talk about. One of the other things is you can have very similar mineralization processes operating in different geological settings, and they produce deposits that look completely different, or at least mostly different. So lots of different things can be controlling that, whether it's chemistry, host rocks, variations in pH, redox, etc. This is just an example from Peter Pollard based on AIG type deposits. And what he's really showing here is the difference in the style of the structural controls and the difference in the mineralogy that you're getting from very deep, so hot, constricted, high pressure environments up to much more near surface environments. It's particularly the same mineral system, but just a different environment. And so when you get to the end of the day, I've put 50% here. 50% of deposits probably don't really fit neatly into deposit classifications. It's probably more like 90%, but I thought I'd just be vaguely diplomatic. And then the last one, pigeonholes can become basket cases, and obviously IOCGs are the classic basket case, where it started off being quite a specific sort of definition, iron oxide breccias with copper and gold, and a lot of these different deposit types, so hematite-rich IOCGs, magnetite-rich IOCGs, definitely fit in there. But there's also mantos, which you see in South America, iron oxide apatite deposits, Tennant Creek deposits, and you see skarns and ISCGs and all sorts of things get thrown in. It can basically be anything that has iron oxide plus or minus copper plus or minus gold, or in some cases not even that. So I think we can probably we need to have these, but we need to really consider a lot of the different variables in sort of assessing how we use deposit models. And I think petrophysics is a good way to do this. So after I've said all that, I think we can all agree that footprints are important in most hydrothermal systems. And all I'm talking about there is, alteration zonation. So you can see here the classic porphyry model here. We've got zonation, potassic, alteration in the core, going out to phyllic, and then propylitic. And sometimes the argillic here, I think, can have magnetite associated with it. Often, excuse me, magnetite's associated with the core. So you can see here, you've got this footprint of basically magnetite destruction, in this case, around the rim of the central part of the alteration system, and a big bullseye in the middle. So that's generally what we think about when we're talking about alteration footprints, alteration halos. But really, when we're talking about halos, it's actually not just geochemical. It can be structural, textural, rheological, and petrophysical zonation. And I really want to sort of get the point across that petrophysical zonation is basically linked to metasomatism, and it's linked to alteration, and it's also linked to structure. So I'm going to try and weave all of that together for you. I think I more or less already said that there. So just to show you a little bit about what I mean, this is a Swan deposit here, so be familiar to that guy over there in particular. You can see here, we can see zonation in the magnetics here. So you've got a fairly broad high in the core of the system. Outside of that, you've sort of got this halo around here, where you've got structurally controlled elevated magnetics, so elevated magnetite sitting around the core. If we cross over here to the first vertical derivative of magnetics, so that's just a filter which picks out the structure a little bit better. You can see here you've got these shear zones running down here, or at least higher strain zones, and they're truncated through here by a different, probably a different generation of structure. And you can see Swan's just sitting right in between those shear bands there. This is a radiometrics ternary image. So in this, red is potassium, blue is uranium, and green is thorium, and the white is just high radiometrics in general. What you can see here is through some of these sort of high strain, possibly shear zones, you can see elevated uranium running through some parts of that, and it's focusing in here, also in that structural corridor. So we don't generally think about geophysics as something that we can use to map all these different elements of mineral systems, but you can see here, you know, the geophysics is giving you evidence of zonation, you're getting structural controls and fluid pathways just from geophysics here. Okay, how do we usually use geophysics though? And I'm taking the mickey a little bit here. I'm probably oversimplifying it, but bullseyes. We circle bullseyes in our magnetic data or our gravity data or EM or whatever it is. We might draw some lines on a map and call them structural controls. We might not go and validate that, or we might go and validate it. We might compare it to a geological map. We might run some inversions, get a forward model, come up with a body, drill a hole, and we either hit something or we don't, and that's probably the end of it. But really, if we actually go and think about the mineral system and the petrophysics and what sort of data we need to collect earlier on in the piece, we could probably do a much better job of geophysics. And the other thing about bullseyes is, you know, some of these are barren magnetite, some of them are mineralized ironstone. It's these ones here. Some of them are different styles of deposits. So we can go and drill bullseyes as much as we like, but we've probably drilled most of the good ones by now. And just because there's a bullseye, it doesn't mean that there's a good mineralization anomaly under it. It's most of the time it's going to be mafic rocks. So this is a slide that Rick Valenta put up quite a while ago now. And Rick was basically saying, we've done all this research in mineral systems and it hasn't really translated to new deposits. And that was fair enough. Rick was trying to get research funding at the time, and I'm sure it served his purpose very well. And I don't disagree with it at all. But I would say, you look at these deposits here, the main deposits that were found, the last main deposits that were found in the Cloncurry district, they're all around there. These are all the undercover ones here. They're all found off the back of, mainly off high resolution airborne geophysics. Not all of them. Some of them were, I think some of them were EM anomalies and various other techniques, but geophysics was a big part of it. You know, and I think we've done a lot of research in economic geology and geochem, structural geology, regolith, I think is one of those CRCs there. But, you know, there hasn't been much on geophysics really. And in fact, most of the research on Cloncurry that's on geophysics, I've probably had a pretty strong hand in a lot of that over the last few years. So I think, you know, not much research on geophysics, no new tier one discoveries. Maybe these two things are linked. And I know I'm pushing a pretty, you know, contentious barrow there, but I'm going to push it anyway. So, you know, can our use of geophysics be more targeted? I think it can. I think we know a lot about these systems. We just don't use it enough. So what controls geophysical signatures? I think that the short answer is petrophysics. Mineralogy controls petrophysics. What controls mineralogy? Lots of different things, obviously. So the main things in terms of magnetics are going to be iron, sulfur, and oxygen content. But then you're also getting into things like redox, pH, temperature, proximity to source. There's a whole bunch of things going on, right? But what this slide really shows is you can have a deposit with the same density, and it's got different proportions of magnetic minerals. You get a very, very different outcome. So monoclinic pyrrhotite dominated system over here, you can get a remnant magnetic anomaly. Magnetite rich system, you're going to get a huge big magnetic anomaly. As you're getting over to the hematite dominated systems, you're potentially getting a very, very subtle magnetic anomaly. And I don't know that many people realize that, you know, hematite is about as magnetic as shale for the most part. It's not very magnetic at all. We'll explore that a bit more. So what is petrophysics? Properties of a rock, things we can plot on XY graphs. A lot of people would stop there. The inverse of geophysics, that's true. But it's a function of three main things, I think. It's geology, mechanics, and chemistry. So petrophysics kind of sits at the core of that. And, you know, I don't need to go through all of this in detail, but I've spoken about some of those to some degree. But structural controls and rheology are incredibly important in what happens with fluids, and the geology is very important in terms of the alteration and, you know, how fluids are moving through those rocks. So I think the geology and the chemistry gives us the why, mechanics and chemistry give us the how, and the geology and mechanics give us the where. And petrophysics can tie all this together, and it also ties it to geophysics. So I think, you know, I think petrophysics is the missing link. I don't think we do enough of it. I've been doing far too much of it, and I understand why people don't want to do it, because it's not necessarily easy. There's a lot of work involved, but it can show us some pretty cool stuff. Okay, so I want to go to one of my pet hate subjects, which is the coincident magnetic gravity high. So a lot of people in AIG-GSAQ exploration will say we're looking for magnetic gravity highs, which is what you'd expect, right? It's magnetite or hematite. It should have a nice density. It should be quite magnetic. And it's true some of the time. So you see Osborne up there, it's incredibly magnetic. And it's incredibly dense. And so anything that's got a lot of magnetite in it, absolutely. Most AIG-GSAQs are nowhere near that. They're still relatively magnetic. They're still quite dense. These are the magnetite-rich ones. When you're getting into ISCGs, so iron sulfide, copper gold systems, where pyrrhotite is the dominant magnetic mineral, these are quite weakly magnetic, or they can have remnants. And then hematite, you're pretty much not really going to have a magnetic anomaly at all, or it's going to be very subtle. So they're not all the same. It's quite obvious, really. But the other thing is gravity data usually won't help you too much. Even if you do have a body there that is dense, it's probably not going to help you most of the time. And I'll talk about that in a second. But this is just some examples of different types of anomalies that you might get with ICG type systems. This is from Brumby. That's just a little prospect sitting up north of Osborne there. And what you can see here, you've got a joint model there, which is basically this model fits the gravity field, and it also fits the magnetic field simultaneously. So it's a coincident source. And that means you've got magnetite. That's pretty obvious. If you go to Prominent Hill, what you see here, you've got the gravity model here that coincides with this gravity anomaly here, this big sort of shark fin type thing, or I don't know what that's called. The magnetic spike over here, that's actually due to a magnetite skarn, according to Hart and Freeman. So here you've got a lateral gradient from magnetite into hematite. If you go to an Olympic Dam here, and this is a very Mickey Mouse model from a long time ago, but I think what this shows is the gravity model here, This is hematite breccia in the near surface that's causing that huge gravity anomaly, whereas the magnetic anomaly is being modelled due to a magnetite-rich source at much greater depth. So here, even though these anomalies are sort of coincident, they're not really coincident with the same bodies. They're overlapping. So it's a maybe a bit of a minor point, but if you think about it, you don't necessarily want to have coincident anomalies. What you really want to have is evidence of zonation in the system, because where you've got zonation, where you've got gradients in redox and temperature and pH, that's where you're dropping out minerals. And I'll show that a bit more. But we're mainly just trying to show here that, you know, coincident anomalies, not necessarily what we're after. So that first example, Brumby there, that's basically a magnetite breccia sitting at the intersection of two faults. At least that's my interpretation. Damo might be able to give you a different interpretation. But what you're seeing here, these are just photographs here. So that's basically actinolite or diopside and magnetite there. So that's a very early sort of calcic, high temperature calcic alteration. That's bringing in pretty much all of the magnetite very early on in the piece, not much mineralization. You've got potassic alteration here, which is overprinting that, and that's actually stripping magnetite out of this brecciaclast here. So you're going to be losing magnetization during this alteration process. You're forming pyrite, and the later stage stuff, it's basically sulfides, chlorite, and calcite. That's pretty typical sort of a paragenesis for an IOCG. But the reason why it's all focused in this one zone is basically all the fluids are going the same pathway. So you're not really seeing the zonation in here. You're passing all the fluids through the same pathway. It's a very discrete zone, and that's probably not really what we want to see. What we want to have is much more structural complexity. We want to see structural controls that are changing over time, creating a larger footprint. And I'll try and illustrate that using Ernest Henry. Am I going too fast? No? Okay. So I spoke before about gravity, why maybe gravity is not really going to help you find density anomalies. And what I've done here, you probably recognize my Mickey Mouse model of Olympic Dam over there. What I've done here is I've desampled the gravity data over this area to make it basically an 8 by 8 kilometer grid. And that's found in, I'm not sure what the percentage is, but it's maybe 50% of Australia or 30% of Australia would have that kind of coverage. So I have been a bit strategic with my placement on some of these just to make sure that the anomaly didn't show up. But if you will just allow me that, when you plot this up, guess what? The biggest deposit in the world is not there. So, you know, resolution plays a huge role, you know, and when we start trying to integrate different data sets together, and we're talking about finding, you know, combined mag-grav highs, the biggest problem we have is that our magnetic data is 1,000 times better resolution than our gravity data. And, you know, unless you're going to go and really fill in that data, or at least get it close over some areas, some of these geophysical approaches are maybe a little bit flawed. Okay, so many of you will have heard some of this spiel before. Hopefully I've refined it over the years, but linking paragenesis to structure through petrophysics. This is based on work we've done at Ernest Henry over probably for 5 years or so. We've sampled maybe 10 to 12 drill holes through the deposit, which are really aimed at covering all the major structures, the major shear zones, the breccia, going from the sort of distal footprint through the medial footprint into the core. both across strike and along strike. And we've collected little samples, paleomagnetic samples, and we're basically trying to do a whole bunch of things at the same time with co-located samples. And this is so we want them to be co-located so that they give us a really good fingerprint of what the system's doing. So it's not about collecting, consistently spaced data to Krieg and extrapolate that way. What we're trying to do is understand the system. We're trying to sample geologically representatively. So we'll look at some rock textures, alteration. We'll look at structural fabrics, petrophysical properties, and a constrained model. So it's really trying to produce an integrated assessment of the geology and how it relates to the geophysics. So here's some, this is just a plot. I'll show a few of these, a plot of susceptibility versus density. I've showed a few before without explaining that, sorry. And I've got some TEMA images over here. So these are SEM images where we're mapping different minerals in here. So this one here, this is basically sodic alteration. It's what, 80% albite in there, titanite, magnetite. This is pretty much everywhere in Cloncurry. It doesn't always have the magnetite associated with it, but it's very regional and pervasive. We have calcic alteration, what I'm going to call calcic alteration, although some people might debate this one, but it's basically actinolite, magnetite, calcite. These are both pretty common in regional geology, so you'll see them in some of the calc-silicate formations quite commonly. These have fairly low susceptibilities, although it can get quite high. There's quite a bit of magnetite in here, but this is pretty consistent with the distal footprint of this system, or it's actually the early part of this system that's still remaining. But nevertheless, densities are quite low, not terribly magnetic compared to some of the other alteration we're seeing. As we go in, you can see here, this is iron apatite alteration. So it's sodic, it's related to the sodic alteration, but it's much more rich in magnetite. So the dark blue there is magnetite, and the pinky color is apatite. And this is pretty common at early stage of an AIG system. You can see there, we're getting very high susceptibilities, very high densities, and most of them are plotting sort of in this area here. Going in a bit further, or maybe going a bit further on in time, we get biotite magnetite alteration. You can see this is overprinting the sodic alteration, and this is a little bit less magnetic, definitely a little bit less magnetic. It's quite a lot less dense, and what you're seeing here, this is sort of the outer part of the potassic alteration at Ernest Henry. So biotite magnetite rich, still sitting along this linear trend, which I call the magnetite trend. Well, it might not be me who made that up, but once we go into getting into the breccia, here we have pretty typical K-feldspar alteration. So it's microcline, quartz, a bit of magnetite, but a lot more muscovite and chamosite, and a little bit of pyrite starting to come in here as well. So here, we're really starting to come off this magnetite trend here in orange. So there's a couple of reasons for that. We're losing magnetite and we're making pyrite, but we're also, this muscovite and chlorite, although they're not incredibly dense, they are adding a little bit of density to this relative to the sort of generic host rocks. So we're kind of coming down in magnetism a bit, but we're mostly just getting denser. Now, the final stage of alteration, which is what Tobias, one of my co-workers, Tobias, calls hydrolytic alteration, quartz, chlorite, calcite, and hematite, and quite a lot of chalcopyrite. So here, all this blue stuff here although it doesn't differentiate it. In this case, this is all hematite. So we're going into the core of the system. We're getting cooler. It's telescoping in. We're forming hematite, so that's oxidizing. When you form hematite, you're actually making a denser mineral, and that creates porosity in this system. And Tobias would say that's a large part of the reason why you're able to bring high-grade copper in very late. Now, this isn't necessarily everywhere in Ernest Henry, but it is the sort of the last phase that we see. And so you can see here a lot of those rocks, they're nowhere near this magnetite trend. So they're basically hematite. And so, yeah. So this is a really busy slide. I won't go through all of it. But I think what I showed you there, based on Louise Corriveau and others' work from the Canadian survey, we're really seeing what they describe as the generic paragenesis of an IOCG. We've got the sodic calcic alteration. We've got the high temperature calcic alteration, iron apatite alteration. We're going into the high temperature potassium ion alteration, which is the biotite magnetite over here. Then into the K feldspar alteration, which is the orange stuff there. And then we're going through this magnetite to hematite transition. So we're going from hot, probably, D2 in Cloncurry, for those familiar, 1585, through D3, D4, potentially getting somewhere near D5. So it's pretty good evidence that it's actually a protracted evolution. You're going from fairly high temperature and pressure to low temperature and pressure. But also with that, and I didn't really touch on this too much, but the kinematics are changing through that as well. So in the earlier phases, the magnetite-rich albite phases, you have shortening in this direction here. You basically have a pure reverse shear along that. I'll show you the shear zone in a second. As the system evolves, the shortening direction rotates around, and you start getting more strike slip movement, and you eventually rotate it around to a point where the strike slip takes over and you actually come under trans tension. And so rather than shearing, initially you're focusing deformation in that zone. When you get to this later phase, you're starting to open up some of these north-south structures and you're splitting this apart. And so my hypothesis is that the mineralization is basically forming at the intersection of those structures. And that's exactly, if you were to go and plot that point on the stereo net and turn it into a vector and put it next to the ore pipe at Ernest Henry, that's exactly where it is. It's exactly on that trend. And that's the case for quite a few other deposits in the Cloncurry district. So another way of saying that is we start off with a constricted system. So high pressure, all these fluids can't easily escape. And then as the pressure decreases, we're focusing albite, actinolite, magnetite, apatite into shear zones. So they're fairly low permeability and low porosity. They're constrained. So it's seeping out slowly, but it's basically forming a lot of magnetite, which is probably giving you a big anomaly to begin with. As we progress, the shear is rotating around. We're getting cooler. We're getting less ductile, more brittle. System is telescoping in. We're getting K feldspar brecciation in the core of the system. And that's giving you a subtle magnetic anomaly. But what it's also doing is it's really leaving the most magnetic parts on the rim. And that's exactly what you see here. You see these high magnetic zones in the Marshall shear zone and the footwall shear zone here. And it's a much more subtle anomaly in the middle. It's still big, but it's a much bigger volume as well. So less magnetic in there. When you're really cracking this system open, you're forming mineralization at the intersection. And if that hydrolytic alteration, that magnetite destructive alteration had gone further, you might even end up with a hole in the middle, a sort of a donut-shaped anomaly. Okay, I think I said all that. I'm sorry if that's a lot to take in, but anyway, you can ask me about it later. So I learned a bit at the structural geology conference a while ago. I think we tend to think about economic geologists, and no offense to any economic geologists in the room, economic geologists like to think about structures and fluids kind of a bit separately. The structure is just like, it's just like a fault miraculously appears just when the fluid is ready, and then you get a deposit. That's what it sounds like to me, anyway. But I think we can assume, we might assume that strain conditions change with pressure, temperature, and depth. But really, I think in hydrothermal fluid systems, it's really all about fluid pressure versus crustal pressure. And it's about the changes in rheology and what that does to fluid pressure. Fluid pressure is going to be a really big driver in how you develop the structures, and then both of those things together really control the geophysics. So that's what's controlling the petrophysics. And I think I'll just move on. So we're getting to the end here. So what I was just showing you then was concentric zonation, which would be fairly typical of sensu stricto IOCG, and it would be fairly typical of a relatively undeformed upright porphyry. But there's lots of other different types of zonation we can see, and some of you guys who've seen some of my talks before would recognize some of these ones here. Some of my favorites, Monakov here, for example, got a beautiful sort of linear anomaly that's very magnetic in the core, and then it's very weakly magnetic on either side. It's kind of a shark fin anomaly. It basically has a sort of magnetite barite copper lode in the middle here, and then you've got magnetite in the host strata at this side, and then finally hematite even further out. So you're seeing zonation from very magnetic to weakly magnetic. This is Moronin here. This is kind of the opposite case, where you've got highly magnetic units on the outer part. You've got structure through the middle here, and these structures are basically bringing in fluids that are demagnetizing the core of that system. And I know you're geologists, not geophysicists, so I'll show you some rocks. Well, I'll show you some petrophysics first. I think I just showed you that. But one thing about the petrophysics here, it's very complicated. You're sort of seeing, evidence of this iron, this hematite-rich ironstone trending out of the Tall Creek volcanics here. You're seeing magnetite sort of enriched sediments related to the Llewellyn Creek formation here. And then the ore zone is sort of just completely doing its own thing, which kind of suggests there's sort of more than one episode, I guess. And here's a selection of some of the rocks from Monakov here. So you can see here we're going from the outer part in, which could be oxidized to reduced. It might be cold to hot, depending on what sort of deposit you think it is. Quartz rich in grey here, and hematite here. You can see a nice reddish color. If you're going in here, you can see the blue bands through there. That's the blue bands is magnetite in that magnetite-rich banded shale there. When you get into the middle of the system, what you're seeing is a barite, calcite, magnetite, manganosite, sphalerite, pyrite, galena assemblage, and some huge chunks of fluorite in there. It doesn't look like any IOCGs I've seen, although you do see elements similar to this in Ernest Henry in some parts, and especially in E1. But there's a lot of magnetite in there, and this one in particular, there's heaps of magnetite in there. But what are you seeing? You're seeing zonation, basically hematite, magnetite, lots of magnetite, and lots of extra dense minerals in there as well. Now with Moronan, as I said, it's a bit of a different, of the opposite scenario. The really magnetic zones here and here, these are basically sort of calcite, what are they? Magnetite, apatite, garnet rocks, which I'll show you in a second. This is just density susceptibility again. You've got pyrrhotite, galena, calcite rocks, which are kind of like skarny type things. I don't know if I want to call them skarns because I could get crucified for saying that, but they're recrystallized, as I'll show you. And then you've got these K feldspar rocks down here, which are very low density and very low susceptibility. And you can see here, this is the mag model. These they're low magnetic zones in there, high magnetic zones there. So from the sort of distal part into the core here, you see that's the magnetic anomaly there. You've got the host rocks, which are pretty boring, sort of muscovite quartz schists. The really magnetic rocks, this is sort of apatite, magnetite, calcite, garnet, all sorts of funny, weird minerals whose names I can't really pronounce there. Pretty high temperature minerals. When we're going into this pyrrhotite, calcite, galena sort of assemblage there. And then there we've got microcline quartz. This is pretty similar to a sort of a potassic breccia that you would see in an IOCG system. So nothing really magnetic, moderately magnetic, and pretty much non-magnetic. And you're seeing the zonation here. This is just basically a leapfrog interpolation of some of the drill data, which Rob Rutherford kindly gave me back in the day. This is the magnetic model here. And you can see you've got this sort of S-shaped fold in there. And then it's cut up by faults through the middle. And the mineralization is basically somewhat zoned, sort of from the lead, the zinc, and the silver there, with the iron mainly on the outside. So again, here you can see the relationship to the structure here. So you see this big S-shaped fold here, and that's wait a second. So we're at Moronan. We're still at Moronan. Sorry, I'm losing my way a bit, am I? It's the same anomaly. You've got the low mag zone in the middle. You can see the structure in here. It's a big S fold, which is probably a very early D1 fold. And that's so probably. Yes, it's just a mirror image of it's a mirror image of a Z. It's a mirror image of a S fold. Stop distracting me. But it's evidence of very early. Yeah, well, that's true. I should be on it, actually. Yeah. I'm just struggling. Yeah. Okay. So you see that S fold, but all these rocks basically have the same fabric. So this is from magnetic fabric measurements. They all have the same fabric, which is that bolt upright fabric, which is very typical of D2. So even though we're seeing structure in here, the actual fabric in the rock is all from the peak metamorphic time D2. And then you've got these later structures in orange here, which are these ones cross-cutting through there. They're the ones associated with the potassic alteration. So I guess what I'm trying to say is you've probably got something which I would say is a very early VHMS system. So it's probably around the time of deposition, 1620, 1640, something around that. and then potentially overprinted by several different types of alteration. But it's this potassic alteration through the core that is mainly killing the magnetism in the middle. So it's not just one alteration system and zonation, it's actually multiple systems overprinting. Do we want to go to the too hard basket or not? Yeah, I think I need some sustenance quickly. All right. So COBAR, how many people have worked in COBAR? Oh, all right, good. Yeah, what a dog's breakfast COBAR is for geophysics. You can see here, these are all paleo channels in here. So that's magnemite in paleo channels. And this stuff, even though you can see it really clearly here, this stuff is absolutely everywhere. There's just less of it here and here. It's absolutely everywhere. You can upward continue this. You could low pass filter this data to 10 kilometers. They're still there. You cannot, there's no geophysical way you can really get rid of it. You're just stuck with it. And you're also generally working under maybe 80 to 200 meters of cover. It's a pretty difficult place to work, I guess. And there's other challenges, which I'll go through. You can, however, see there's one main corridor just in there, that's the main sort of mineralization corridor at COBAR. That's where most of the main deposits are found. So we are seeing something in the mag, and I'll just tell you what that is quickly. So here, unlike at Cloncurry, where magnetite is basically the main magnetic mineral, what we're talking about here, it's mainly pyrrhotite. There is magnetite. You can see here, I think it's mainly the same color system we've used. So it's quartz in gray, blue is magnetite, green is chlorite. So we've got this sort of magnetite chlorite assemblage, which is pretty early in the piece. Not much mineralization associated with it. And then it's overprinted by other types of assemblages. You've got pyrite here, chalcopyrite, the bit of pyrrhotite and anchorite and calcite. So it's basically early. What it is a reactant. It's providing redox potential for overprinting sulfides.
Where is the sample from?
Where is the sample from? Yeah, that's a good question. What deposit? That one's from Chesney. Yeah, sorry. I'm skipping over things. Yeah, so that one's from Chesney there. That's from Jubilee, and that's from Mount Pleasant. But yeah, so all through that corridor, though, you'll find magnetite in those ore deposits. And you can model this up. So Giovanni Spampanato has done a few voxel models through that same corridor there. And what you can see is that the voxel models, which are showing, it's just a voxel model indicating where the magnetization is. It basically has a sort of a inverse relationship to where the copper is. So that agrees with basically what you're seeing in the TEMA imagery here, that the magnetite is there early. The structure's cross-cutting this main corridor, replacing part of the magnetite, and so the sulfide mineralization is overprinting magnetite. So if you're going to go around chasing bullseye anomalies here, you're probably going to find that stuff mainly. It's not really what I wanted to talk about, though. Most of what you see out here is pyrrhotite. And when it comes to geophysics, pyrrhotite is a lot more challenging. So the pyrrhotite's in red here. Here you can see it associated with zinc in green here. And in the light green there is galena. So that's basically like a VHMS type horizon from Mallee Bull. You can see it associated with skarn and this one is from, I think this is from Nymagee. It's from Nymagee or Federation, this one. Here, this is like a retrograde skarn. It's got chlorite in there. The pink little things there are titanite, and this is hexagonal pyrrhotite. So this is basically formed from a fluid. It's crystallized from a fluid, and it's adopted that hexagonal structure, which is non-magnetic. Mostly what we see is very strongly sheared pyrrhotite. So you see it all throughout the country rocks, and you see it in some of these copper breccias as well. So this is all the magnetic form, and I think I'll just move on. I talked about alteration gradients before. The alteration gradients you see in Mallee Bull, for example. So we're talking about Mallee Bull, whether it's a VHMS or whether it's an epithermal or whatever. It has alteration which is consistent with porphyry type system. You've got basically chlorite and quartz in the base, grading up into much more muscovite dominant in the top. You're seeing copper breccias and copper stringers in the base of the system, and you're seeing this VHMS style mineralization up in the top, proximal to where you're seeing the pyrrhotite here. You're also seeing gradients in the titanite phases. And I'm not really a geochemist, but John Walsh assures me that that's an indicator of a redox gradient when you're seeing that type of behavior. But I'm not going to focus on that. What I want to show you here is just the geophysics, the stuff I'm actually good at, or better at. What you can see here, this is just a model based on the gravity data. And you can see here, it's showing up these faults quite well. This is Mallee Bull, by the way. You can see here these faults offsetting this anticlinal structure through the middle there. That's the VHMS style mineralization, the main lead zinc style mineralization. The thing I want you to see here is that basically the gravity anomaly is not picking out the mineralization at all. It's just picking out the stratigraphy. So basically a 0.01 contrast in the density here is enough to give you that gravity anomaly. You've got massive sulfide ore here, which is a density, around 5, which is big in terms of gravity, but it's basically a few meters across and it's 200-300 meters depth. So not showing up in the gravity at all. If you go to the magnetic data over here, it's almost a little bit of an inverse scenario, but it's not really showing up this either. I think that's probably a shed, that little spike there, or a grain bin or something like that. What I do want to draw you to, though, I should point out that lights up like a Christmas tree in EM data, and that's how they found it. It doesn't show up in IP. Some of that copper pyrrhotite breccia that I was showing does show up in the IP. So different parts of the system respond to different things, but neither of them really show up to mag or gravity. This anomaly here, though, you notice it has a very big low here. I just want to explore that quickly for my last slide. Second last slide. So that anomaly we were just looking at there, you can see that you've got the high here and then you've got the big low. You can see that here as well. So when we've done a reduction to pole magnetic transformation, what that really should do, if this is like magnetite, for example, or a purely induced magnetic source, that should center over the source. Now, if we have remnants, so pyrrhotite can be very strongly remnant, then the RTP is not going to work. And so you can see here, this still looks like it's a remnant anomaly. You've got this dipole effect, high mag here, the high here and the low here. So you can use a technique called an analytic signal to hopefully correct for that somewhat. Or you can use a filter called a normalized source strength filter. And this is what this is doing is basically it's removing, it's devectorizing the magnetic properties essentially. So it's just saying, where is all the magnetic stuff here? Saying, well, the magnetic stuff is there. And if that was exactly the same as what we were seeing in the RTP, we would say it's probably all magnetized. It's all induced magnetization. But yeah. Well, that's the VHMS part of Malibu. Yeah, it's probably, well, there you go. Oh, look, there's a scale bar. Yeah, yeah. Well, it's going to be, yeah, it's going to be about 1 kilometre across. So.
Yeah, those two panels.
Yeah, they're the same as the exact same grid as that. It's just in 2D.
Yeah. The 2D. So Malibu lies where on the right there.
Up around there. Yeah. But that's the VHMS. So that's the lead zinc load, which is the massive sulfide. That's where that sits. But I think what this is showing us is that actually most of the magnetization is centered off to the southeast of that. So this is, I think this is showing us that we have a whole bunch of pyrrhotite dominated alteration, which is focused by all these faults in here. And you see remnants like this all throughout the Cobar area. We know it all has pretty much the same direction, and it's sitting in pyrrhotite. And if I go back a few slides, a lot of that pyrrhotite is sitting in here with these copper breccias. So, you know, I wonder if maybe coming down here, you might be getting closer to the core of that system. You know, it could be a porphyry sitting under that even, I don't know. But the point is, if we can take on some of that complexity, and we can think about some of these complex things like remnants, think outside the box a little bit, there's still potentially gains to be made, you know. We just need to, I think, you know, sort of, you know, I don't know, just think about what we're looking for rather than just chasing bullseyes, I guess. I don't know that's idealistic, and it's coming from someone who doesn't really do exploration, who just gets to do forensic studies on ore deposits 20 years after they were discovered. But there must be something we can take out of this type of work that can help us to do more effective exploration with geophysics. All right, so we're at the end. So the takeaways are, don't take deposit models too seriously. Probably don't take geophysical models too seriously either. They only work sometimes. If you think about the processes, structural metasomatic processes in particular, and how they could really control the system, that'll take you a long way towards understanding geophysics as well. Yeah, and one from Terry Harvey. You know, coincident anomalies probably equal mafic rock most of the time. I used to keep getting up in Cloncurry and saying, you know, we need more gravity, and he's like, oh, yeah, gravity just finds mafic rocks, Jim. And I think I finally agree, Terry. But you know, I think zonation is key. Zonation is really what we're after. We don't necessarily want to find coincident anomalies. What we want to find is evidence of zonation, because that's evidence that we've got gradients in redox, or it's evidence that we've got zonation proximal to a vent, for example. It's the complexity that we're trying to identify. And I think I'll leave it there. Thank you for paying attention. Sorry if I lost my way a little bit there in the middle, but thank you.
Thank you. Any questions? Thank you.
Sorry about
Yeah, I just wondering, you mentioned high resolution gravity, so like what do you think angle gravity radiometries are useful there, or you take to
Yeah, I mean, it would be great if we had more airborne gravity gradiometry, for sure. It does have a few different challenges, though, in that you're not actually measuring the field, you're measuring the gradient, and that sort of means you're not quite getting the same sort of depth penetration, I guess. But the noise is a consideration. But I mean, I would really like to see a lot more gravity, whatever shape it comes in.
Thank you, Jim. Just early in your talk, you mentioned the fact that there hasn't been enough research into geophysics. Can you actually just explain a little bit more about where that research should be going with respect to geophysics?
I think I don't know if I meant geophysics. I think a lot of research does go into geophysics, but mainly into developing software. And sometimes that software development is kind of circumventing physics rather than really utilizing physics. So I think I probably meant more research on petrophysics, or more research on petrophysics, which is really the link between geology and geophysics. I think that's a critical thing. We've as a community, we've been talking about doing more petrophysics for at least as long as I've been in CSIRO, but it hasn't really translated into more people doing it. And the companies do it. I don't know what they get out of it. I'm not sure if many companies know what they get out of it either. I think it's just something that gets collected and forgotten a lot of the time. But there's ways you can do it well. It needs a small army, though. That's the thing.
Wait. I'll just go. No, wait. Oh, no.
Short question from the audience. How have integrated geophysical data sets helped reduce uncertainty in drill targeting the Concari region?
How can they do integrated data sets? How can they reduce uncertainty? Yeah. Well, well, it depends on what you're talking about, I guess. When I'm sort of thinking about petrophysics, what I'm thinking about is really trying to fingerprint the system, so you know what the physical properties are of the different types of alteration. You need to tie that with structure, obviously. You need to tie it all together. But I think it is critical to get a good understanding of the different types of rocks you have. If you understand the physical, I guess, the physics of what you're looking for. I'm tying myself in knots here, aren't I? But I mean, it has to be part of a sort of a broader integrated solution. But I didn't really show much of the magnetic fabrics. But if you can tie the magnetic fabrics to the structure using geophysics, you can tie the alteration to the magnetic fabrics. It's really about trying to tie everything together sort of more holistically. So you can sort of translate that into petrophysics, and then you can model it using geophysics. Even I think that what I just said was a bit of like massive arm wave. But I'll have a chat with you about it separately, maybe. It's a 1 hour. There's a potential 1 hour question answer in that, but I'm cooked.
Earlier, when you talked disparity between the spatial resolution of magnetic data and gravity data, you made a point of it. I'm just wondering, what about the disparity in the dynamic ranges of the two types of physical parameter? Is it going to matter if we get spatial resolution that's equivalent? Because between a dense ore body and a just normal rock, there's not a huge contrast between a magnetic block of rock and a non-magnetic block. There's a far greater dynamic range, many. So how's that going to play out? I'm suggesting. And what about if you're going to get a tighter spatial resolution with gravity, are you going to have greater detection limits in the instrumentation to make use of that?
Yeah, definitely. If you're talking about gravity gradiometry, yeah, I think if you wanted to go higher resolution. Well, I mean, the conventional gravity should have the precision to do it, but you're absolutely right about the dynamic ranges. Like I was just talking with the Rio guys today. Like globally, densities vary by half an order of magnitude. Magnetic susceptibility can vary by 7 orders of magnitude over a couple of millimeters. So it's absolutely. It's just the cost. I think it's the cost. Well, I think that the fact that it costs 1,000 times more to collect and there's 1,000 times less of it, I reckon, is a pretty good.
Positional location technology.
But what you just mentioned, though, is very valid for collecting petrophysics downhole as well. Like, because in hydrothermal systems like IOCG systems, there's a huge nugget factor with the susceptibility based on where you have magnetite or where you don't. So you really, to get a good answer, you kind of need to collect quite a lot more downhole susceptibility than you do gravity, just because it varies. It just varies so much more.
Question from me, our geological surveys do a fantastic job of collecting data. It's been a lot of emphasis made with MT and AEM on regional scale. Seeing what we've seen tonight, is this still a little bit misplaced? Should we, to my mind, magnetics is a much better proxy for geology, structure, and alteration. We just need to get better at interpreting that data properly rather than just a couple of lines, a couple of servers.
We could definitely do that. Yeah, I mean, I should have said before, the Geological Survey of Queensland paid for most of that work. Obviously, not the stuff in New South Wales, but that was the New South Wales survey who's funded that stuff in Cobar. They do great work. They're pretty thin on the ground, though. But there's heaps more we can get out of, even just filtering out different wavelengths of data out of magnetic data sets. You can get a lot out of it. You have to do that in an area like a Cobar, but yeah, where you don't have to do it, you tend not to do it. But yeah, you can always get a lot more out of it. You just need some really detail focused people who want to lock themselves in a room for a while and do it, basically. Or, I mean, we should be able to program AI to do all that stuff for us automatically, shouldn't we?
Thank you.
Just thinking, was there any research that's been done into like downhole gravity or geophysics linking to things like geotechnical domains or communication performance? Like looking at SG and hardness, how it goes through a well, that's good for mining kind of thing?
Yeah, we could do that. The problem for us is, companies will collect a lot of 1 or 2 types of data, and we collect a small amount of samples, and we collect lots of different types of data on it. So where like this sort of approach is not really designed to do that. It's really designed to more like fingerprint the system to get co-located data sets to sort of characterize the mineral system. There's no reason why you can't do that. It's just it's probably not, it's not our domain. Yeah, I guess you should be using it for whatever you can use it for.
Jim, thank you. I'm going to ask you a money question. Management. I'm a geologist, but I'm also running a mine. Right? The exploration guys use geophysics all the time. I don't understand half of it, not a quarter of it. So they want to go and drill the hole. How do I get to that decision? Drilling the hole.
Well, you could just put a circle around a bullseye. There's many ways to skin that cat, I guess. But show me where you're exploring, and I'm happy to throw my 2 cents worth in. But the thing about exploration is what you need to do in one area is completely different to what you need to do in another area. No, you can't have just a one size fits all approach to it. Like in some cases, structure is going to be really super important. In other cases, host rock's going to be really important, and all variations thereof. So, but one thing though, if you can collect samples and you can characterize those samples and you can understand the physics of those samples based on one drill hole, for example, if you can go and collect some data early on, that can make a huge difference to how you interpret your area. So like me coming along 20, 30 years after they found those deposits and figuring them all out, does it help? It could help, but it'd be better to do it after you've drilled one hole. Okay? That's where you get the most benefit out of it, I think. This is going to be a cheeky one, isn't it? I can tell, but no.
And normally targets, totally, but it goes back to what's in the top. All models of rocks are useful, and we make a bunch of assumptions. Right? What think is the geological and the geophysics and the structure, and then we put a hole in it and change it. So to me, these days, downhole geophysics early, feeding back in the models, which is not just a straight inversion, but it's like Jim's been saying, geology, structure, physics, all that type of. That's where the decision making comes.
Yeah, I think it's
in relation to the question on using physics for convolution and other aspects of downstream processing. Absolutely. Very cool. Just make the data.
I think people do it, yeah.
Yeah.
Just we don't. That's all I meant.
Well, I think we might
warn them out.
So thanks once again for coming all the way.
And thanks to Peter for the invite, even though the invite was probably 3 years ago. And thank you to everyone for coming. I hope I didn't sort of gloss over too much of it, but I really appreciate you all coming, and nice to see you all. Thank you.